do it once we get on Screencast-O-Matic. It's just a minor thing, but it's just a minor change to my office hours just for tomorrow. Yesterday I said I had a doctor's appointment. That wiped out my trig class. So tomorrow, unless when I meet tomorrow morning, if they can't do it, but I'm planning till tomorrow, we'll have class from 9:30 till 10:45, and then immediately do 10:45 to 12 o'clock to make up the class I missed because of my doctor's appointment. Now, if they can't do that, we'll do it the following Tuesday. But as far as I know, right now I'm planning to, normally on Thursdays I have office hours from 10:45 to 12:30. Tomorrow it's going to be 12 to 12:30, unless they can't meet that backup. Not everybody can meet, but I want at least somebody to be there. All right. Any questions on anything we've done up till now? All right. Now, I think last time I asked, and y'all said you like doing the preliminary questions. Maybe the people who aren't here were the ones who liked it, but I'm going to do them anyway because you said to. So these are on the bottom of page 69. And the first one of these is, what is the limit of f of x? Let me get my pen color changed. Okay. What is the limit? Oh, yeah, I'm sorry. I need to turn that on and then I get to talking. There it is. Okay. This one is, what is the limit of f of x is equal to 1 as x approaches pi? Okay. I've basically written down the answer. I didn't mean to. Okay. Okay. Let's write it this way. Okay. Let's start here. F of x is equal to 1. So what's the limit of f of x as x approaches pi? The limit of f of x as x approaches pi. Okay. Picture, you don't have to do it, but just mentally draw the graph of f of x equal 1. What would that be? Okay. Okay, it's a line, but when you say up, I didn't know what you meant by that. What line does that mean? Okay, that would be x equal 1 would be vertical. F of x equal 1. F of x is y. Y is equal to 1 would be horizontal. Y is equal to 1, right? So what's happening is x is approaching pi. What's the y value? No. It's 1. It's always 1. No matter what you're approaching, it's 1. Because f of x is a constant function 1, so the limit of f of x as x approaches pi would be 1, because it's a constant function. By the way, these preliminary questions do have, or some of them anyway, have answers in the back if you want to check. Goodness gracious, these pages are hard to turn. Here we go. 2, 1, the graph, ooh, this is 2, 2, I'm sorry. 2, 2 preliminary question, 1. Okay. All right. The second one. What is the limit of g of t, okay, g of t is equal to t. So what's the limit of g of t as t approaches pi? What would that be? Okay. Yeah. Okay, here's the other way to write this. That's the limit as t approaches pi of t, because g of t is, G of t is equal to t, so that's what we're asking for. And what's that limit? Okay, and as t is approaching pi, what is t approaching? No, t is t.
I'm sorry. You said as the limit of t is approaching pi.
As t approaches pi. Pi is a number, t is a variable. What's the limit of that function? And the g of t, by the way, that's your identity function, right? It's the 45-degree angle through the origin in positive direction. That's your identity function. And what's the limit of that as pi, as t is approaching pi? 1. The slope is 1. As t is approaching pi, because g of t is equal to t, then g of t would be approaching pi. Yeah, pi is right, exactly. Because in this case, the g of t is your identity function, t, going at the slope of 1 here. So as t is approaching pi here, it would be approaching pi here too. Because g of t is equal to yes, exactly. And yeah, basically, the limit of t as t approaches pi would be pi, because t is getting closer and closer to pi. So t would be getting closer and closer to pi. Exactly. Okay. That's the second one. Let's do number 3. Is the limit as x approaches 10 of the number 20, is that equal to 10 or is it equal to 20? Choice. No, wait, not 10. 20 never changes. Your function is 20. Now, it's not 10, or 1, it's 20.
So as
the function is 20. And as x is approaching 10, this function is still 20, right? Because this is a constant function. The limit as x approaches 10. See, there's no x in here. There's no x to change the value. That value is 20, it's going to stay 20. So this will be 20. Now, if that was an x here, the limit of x as x is approaching 10, that would be 10. But the limit of 20 as x approaches 10, 20 is 20. It's not ever going to change. That's a constant function. So whatever x is approaching, negative 10, pi, whatever, this is always 20. Always 20. So that would be 20. Okay. A limit, okay, there's the formal mathematical definition. I think we've already hit that. Do you really want that one? Yeah. Okay. It would be whatever's inside there is usually a function. That happens to be the constant function. Okay. So the thing is, what is happening to that function as x is approaching the, see, this is a element in your domain of that function. This function is 20. It's good for all real numbers. And this is as x is approaching that value on the x-axis, what is that function doing? So it's the identity function. When x is approaching a number, y is approaching that same number. Okay? When it's a constant function, as x approaches any number, this is still that number, that constant value. Now, if that were, say, x over x, okay? If that was the function you had, well, x over x is 1, so that's a constant function. Well, let's see. Trying to think of or x over x plus 2, or something like that. as x is approaching anything other than, did I say x plus 2? Yeah, x plus 2. As x is approaching anything other than negative 2, then it's whatever value you draw that. Okay, let's do that. If your function, the limit as x is approaching something of the function x over x plus 2. Okay? Now, give me a something to put in there. Say again? 3. Okay? As x approaches 3, that numerator is approaching 3, so this would be 3, and the denominator would be approaching x plus 2. If x is approaching 3, that would be approaching 3 plus 2 is 5. Exactly. That would be the limit. Okay? Now, how about the limit of that same function as x approaches negative 3? Negative 1. 3. So that would be 3. Absolutely. So what's the limit of that function as x is approaching negative 2? Undefined, it has no limit.
I took A PKL
Right.
and pre-KL in
Right.
school. So I remember this stuff, but sometimes it gets blurred.
Yeah, exactly. So this would be has no limit because that is approaching 0. It's completely undefined. Now, here's where things gets a little stranger. Okay? What if we had the limit of okay, what would that one be?
That would be 0 on top.
Is what?
0
0 on top?
and
0 on the bottom. Now that is not undefined. We used to call it, we call it indeterminate. So we don't know right off the top until we do some fiddling with it. Can we fiddle with that any? You can factor that numerator. So this would be the limit as x approaches negative 2, and that factor would be what? Plus 2 times x minus 2 over x plus 2. And what can we do with that? Divide out the x plus 2's, and then you would have the limit as x approaches negative 2 of x minus 2, and that would be negative 4. That does have a limit, okay, as x is approaching negative 2, but this doesn't mean it's ever equal to it. X equal negative 2 is still not defined. You have a hole in the graph there. But the rest of it will be there. So if you were to graph that one, do the math like you just did, x minus 2, that would have a y-intercept of 2, and it would have a slope of 1. So it would be like this, but at x equal negative 2, it'd have a hole in the graph. Yeah. No.
The holes come of that power.
Huh?
And then you got the hole out.
Oh, wait, I drew that wrong. I was starting to draw it right, and then for some reason I screwed myself up. Oh, goodness, the eraser's not working. It's not working. There it goes. Okay. I drew that one wrong. It has a y-intercept of minus 2. There we go. All right. Okay, the y-intercept would be minus 2, and then it has a slope of 1. But at x equal negative 2, it has a hole in the graph. Why? Because in your original problem, x cannot equal negative 2. Even though this graph is a straight line, once you do the math on it, and it would go through here, the limit is negative 4. And that would be true because it's negative 3, negative 4. But the actual function is not defined as x equals negative 2. So that's really what we mean by a limit. What is the function approaching, even though we know it can't actually get there? Because you can't divide by negative 2. You have to divide by 0. But x is negative 2. But from both sides, the limit is negative 4. Negative 4 coming in here, negative 4 here. So even though we can't evaluate it at negative 2, you can when you get it in this form, but you couldn't have x equal negative 2 there, then the limit still exists, even though the function value doesn't exist. So that's what a limit is. If something is, from the left and the right, is approaching some value, and those values are the same, even though it's not defined at that value, then the limit exists, and that's what it tells you. And you do run into this in real life. Well, when you're taking an instantaneous velocity, or the slope of a tangent line, the slope is rise over run, right? But guess what? In this tangent line, okay, a secant line has a point here and a point here. You can do change of y over change of x. But a tangent line, there is no change of x. It's at that point. So what is that slope of the tangent line? It's the limit of that, basically 0 over 0. Okay, that's what a limit does. And before you can do that, and see, that's what a derivative tells you is the limit as x approaches, as your dx approaches 0. You can't do derivatives unless you deal with limits. Now, in reality, once we get the rules for doing derivatives, you forget about that you're really doing a limit, but always you are. Because if you think about it, slope is, have you seen this notation for change of y over change of x? Yeah. And slope is that. But what a derivative is if you think about that notation, it's dy over dx. That's gracious. And what it's doing is letting that delta x, which is a finite difference here, go closer and closer to 0. And as it approaches 0, dy dx is in the slope, not of the secant line, but of the tangent line. See, this implies there's 2 y's and 2 x's. This implies you got 1 y and 1 x. What is that change when you don't have anything to subtract? It's the limit of this as that delta x goes to 0. Which doesn't really, you can't let it equal 0, but you can take the limit when it's approaching 0. So that's what it does. And Newton had to do this to get instantaneous velocities, and to get he needed instantaneous velocities to do his laws of motion. And so he had to develop a whole new math, calculus. They said Leibniz did it at the same time, but there's a lot of arguments there. All right. What I forgot to do was go back and check and make sure we had gotten the answers right. I'm sure we had. The first was 1, the second was pi, and the third one's 20. Yeah. Okay. I didn't circle it, but that was their answer. Number 4. I'm going to clear all this off. Is it okay? Okay, to clear it? All right. All right, to erase all this? Okay. I'm sorry, I can't hear well. Okay, number 4. Can f of x approach a limit as x approaches c if f of c is undefined? Can f of x approach some limit L as x approaches c if f of c is undefined? Okay? Now, I'm now sorry that I've introduced the other technologies, terminology. I've been saying -2 over 0 is undefined. I've been saying 0 over 0 is indeterminate. This book doesn't use that term indeterminate. 0 over 0 would be still undefined. But, anytime you divide by 0 is undefined. But I like to call that indeterminate because if that's 0 over 0 may or may not have a limit. Sometimes it does. And the one we just gave would be the example. X squared minus 4 over x plus 2. We know that that's undefined when x is equal to -2. You can't divide by you can't divide by 0. But the limit still exists. It was -4, according to. I wish I hadn't erased that now, because that was the same example. So yes, f of x can approach a limit. It doesn't say it's equal to it. It can approach a limit as x approaches c if f of c is undefined. And the one that we just did was an example. Let's see what example they give in the back if they give one. They give one very close. They say yes, and their example was this one. Very close. X squared minus 9 over x minus 3. As x is approaching 3, that is undefined. Technically, I say it's indeterminate, but that's still undefined. You can't divide by 0. Minus 9, yeah. Okay? But that would be an indeterminate form in my terminology because it's 0 over 0. Now, that doesn't guarantee that the limit exists, but you can process that, and that would be plus 3 times x minus 3 over x minus 3. These go out. You lose that 0 in the denominator. And now, as x is approaching 3, this is approaching 6. So that limit does exist. The limit can exist even so the value is not defined. F of 3 is not defined because you can't divide by 0. But the limit exists because when you did that manipulation, you see that either way you're approaching 6. The limit exists even though the function doesn't.
So the function exists, but the limit doesn't.
Yes. Yeah. Okay. Now, number 5. What does the following table suggest about the limit as x approaches 1 from the negative side of f of x, and the limit as f approaches 1 from the positive side of f of x? Here, you've got your, well, let's see, does everybody in the class have a book yet? I'm trying to remember. I don't know about Nathan, so maybe I better go on and do it. Okay. Here's a table. I think I'll erase. Yeah, it's on the book, but I can't remember if all the students have books yet. If they don't, I need to write it down for them. Okay. Here's a table. X, f of x. 0.9, 7, 0.99, 25, 0.999, 4317. 1.1, 3.0126, 1.01, 3.0047, and 1, 1.001, 3.001, 3.0011. All right. Now, what does this table suggest about the limit as x approaches 1 from the lower side, from the left-hand side of f of x? And what does it suggest about the limit as x approaches 1, but from the upper side of f of x? What would you say? As it's approaching 1 from the lower side. It's what? No, okay. From the lower side, 0.9, 0.99, 0.999, it's getting closer and closer to 1. From the lower side of 1, from the minus side of 1. But look at your F values. 7, 25, 4,317. No. You're talking from the upper side. From the lower side, this is approaching 1 from the lower side. 0.9, 0.99, 0.999. And look at the values for F. They're blowing up. So this is not right notation, but some people would write infinity, positive infinity. I would say does not exist. Okay? Because it's getting big. It's not approaching anything. It's getting enormously large. But as the limit as x approaches 1 from the positive side, getting closer and closer to 1 there, you're absolutely right. That limit appears to be 3. And that, I think you could safely say, was 3. It was close to 3 at 1.1. At 1.01, it was really close to 3. At 1.001 is really, really, really close to 3. So yeah, I think you could say that limit is 3, but this one doesn't exist because it's blowing up. Now, what does that tell you about the limit as x approaches 1 of f of x? If these two limits, unless both of them existed, and they both equal the same thing, the limit as x approaches 1 does not exist. So it would be it does not exist. Now, if this one had been 7, or let's say 7.25, 7.05, and 7.0005, yeah, that would be approaching 7, that would be approaching 3, but then the limit as x approaches 1 both ways doesn't exist because they're different values. This one doesn't exist at all, so the limit, now they weren't asking that, but I was just throwing that in. So what they're asking for, what does the following table tell you about those two limits? The first one, whoops, I'm in the wrong thing. The first one says the limit as x approaches minus 1 from the minus side of f of x, they say is equal to infinity. I don't like that terminology. I'd say it doesn't exist. But the other one is approaching 3. You're absolutely right. Okay. So the limit overall as x approaches 1 doesn't exist either. And that one you can't say is approaching infinity. You say it does not exist. All right, let's do number 6. Can you tell whether the limit as x approaches 5 of f of x exists from a plot goodness gracious, from a plot of f of x, plot of f for x greater than 5. If that's all you have, goodness, this is aggravating. Okay, if that's all you have, if you have the plot of f of x, but for only x greater than 5, and looking at that, and even if it does look like it's coming to a value, if it looks like it's coming to a value, can you say that exists? No, you would have to have the plot showing. Okay, that's not the reason. Yeah, you don't know what it is at 5, but you see what it is for all x's greater than 5. And what it's doing all sorts of weird things, but it seems to be coming in and approaching the value there. Okay? You still can't say the limit of alpha of x as x approaches 5 because you don't know what's happening over here. If all you have is the right-hand side and you don't have the left-hand side, you can't say it exists. Because this one could be doing weird things coming in down here, and this one up here, and x equals 5, it doesn't have a limit. Even though it looked like it did from the right-hand side. It's sort of like that one above.
So both sides
they have to be equal. They both have to exist, and they both have to be equal. This one, the right-hand side existed, and if you had that picture, and only that picture, then it would look like it has a limit of 3. But if you threw this picture in here and found out it's blowing up, no, the limit at x equals 1 would not exist. Same thing. So the answer should be no, you'd have to see what it's doing on the other side as well. Yes. Right. Okay. Well, what I'll do, I'll just keep teaching, even if no one's in here. It'll be recorded, so you can pick that up. And hopefully, by this afternoon sometime, it should be out there on on YouTube. I'm going to try to get it. What's that? Yeah, if you go to Blackboard and go to Content, and I meant to say this, that is something I did get done since last time. Go to Content. Under Content, you will see your syllabus, research paper instructions, my locator card. You'll see a few sites that either I found or students have found that told me they found them helpful. You'll find the YouTube. You'll find the PowerPoints there for all the chapters we'll be doing. And then, I don't remember where it is then, probably before the PowerPoint, you'll see one that says, Math 125 YouTube videos. And if you click on that one, you go to the playlist, and you will see the first, I think you'll see the first 3 that we've done. You see 2 or 3? Just 2, okay. The one that we did Monday, I haven't put out there yet. So, but I'll try to put Mondays and today's out there today.
And will your test be like this?
What's
like
that?
The stuff that we're doing now?
What's
like
that now?
Will your test be like
The test will be more like the homework exercises. These things we're doing right now are the preliminary questions. We sort of get you into the concept of it more than the actual mechanics of it. The test will be a little more mechanics. All right. We did number 6, and the answer was no. You'd have to see what's going on the other side, too. Number 7, if you know in advance, okay, this is a different problem. If you know in advance that the limit of f of x as x approaches 5 does exist, so you know this exact, ahead of time, can you determine the value from a plot of f for all, So if you know this exists, then and you have a plot of this, then can you tell what that limit is? Yeah, that will be that value. Because if the limit exists on the right and the limit exists, period, you know it has to exist on the left as well. You're absolutely right. That one will be a yes. Okay? And number 7 is yes. Number 6 was no, but number 7 is yes. All right, I think I already made all the homework assignments from 2 point. Huh?
I said, how would you do number 1?
One more time, say it.
I said, how
Number 1 in the exercises? Okay, we can do that.
When I say after the bottom and figure top.
Okay. Okay, number 1, you're talking about on page 70. Okay. What it's telling you to do then, fill in the table and guess the value of the limit. So it's giving you all sorts of numbers close, very, very, very close to 1. 1.002, 1.001, 1.0005, 1.0001. Okay. And you find the f of x from that formula up above. Okay. Plugging that in. 1.002 cubed minus 1 divided by 1.002 squared minus 1. Okay. And then you do it for each one of them. See if you can figure out what the limit is. Okay? Now, do it for those on the upper side and those on the lower side. You should get the same answer. Now, if your question was, how can you do it analytically? Yeah, that to me is a lot easier. Okay? And I don't know. I think they're just wanting you to see that indeed the limits exist. Here's how you calculate it. They give you f of x is equal to x cubed minus 1 over x squared minus 1. And what they're asking for is the limit as x approaches 1 of that thing, x cubed minus 1 over x squared minus 1. If you try to plug in the x there, you'll get 0 over 0. Second? So you have to factor, okay? That is an indeterminate form. Let's see if we can get it any better than that. Do you remember how to factor the difference of two perfect cubes? Okay. Here's my shorthand for it. Take the cube root of the first term, that would be x. Keep the sign, minus. Cube root of 1 is 1. All right. Now, to get the second factor, it's going to be a trinomial, always. And here's what you do. Square the first term, x squared, opposite the product of the two, plus x. And then the square of the last term, which would be plus 1. Okay? Now, if you don't believe that, multiply it out and see. X times x squared would be x cubed. Got that. X times x would be x squared, but x squared times minus 1 would be minus x squared. So those add to 0. Then x times 1 would be x, but negative 1 times x would be minus x. So those add to 0. And then minus 1 times plus 1 would be minus 1. Yep, that is the factorization. Okay? Now, you know how to do the factorization of two different. That would be what? Okay? And now you see the x minus 1s can go out. So that gives you the limit as x approaches 1 of x squared plus x plus 1 over x plus 1. Okay? What would that be? Let's try plugging that one in. 3 on the top. There's your limit. You could leave it 3 halves, but if you had plugged in and put in all those numbers, not here, but you know, the one in the table in the book, you would see it's getting closer and closer to 1.5. I find this a lot easier than doing that. Okay, a lot easier. But they really wanted you to plug in the numbers and do the calculations. Wear out your finger in your calculator, but you would see it's getting closer and closer to 1.5, both from the left and from the right. Okay. So I like to discuss. If I can do it analytically, I like to do it because to me it's so much easier. Okay. But you're not supposed to do that yet. All right.
How did you do 23?
23.
I'm thinking I just
Okay, let me see. Let me read what 23 is. In exercises 17 through 38, estimate the limit numerically or state that the limit doesn't exist. If infinite, state whether the one-sided limits are infinite or are positive infinity or negative infinity. Yeah. All right. Let me go and erase this one. And by the way, I should have labeled this. This is page 70. And this was exercise 2.2. Okay. And this was number 1. Okay. Now, I've got that down. Now I'm going to erase it all. Sorry. I should have written that first. So let's do the same thing. Same page. Same set of exercises. But which one did you say? 23. 23. All right. What we're asking for here is the limit as x approaches 0 of cosine theta minus 1 over theta. Okay. Now, did I write it right? I think so. Yeah. Now, what would be your first step? First thing to try? Plug it in, plug it in. And when you do that, cosine theta is, cosine of 0 is 1 minus 1 is 0 over 1. No, I'm sorry, over 0, sorry. I'm sorry, I wasn't thinking. It's 1 over 0. Hey, quit that. Eraser, okay, there it is, sorry. I was talking faster now. As theta approaches 0, that would be 0. So this is an indeterminate form. We don't know if it's infinity, minus infinity, 1 plus or 1 minus, or if the limit really does exist, okay? Estimate the limit numerically or state that the limit does not exist. If infinite, state whether the one-sided limits are positive or negative infinity. So what we've got to do is try to figure out if we can figure this out. I think what they wanted you to do was set up a table and try it that way. Okay? Now, I'm going to suggest something else. Now, this is beyond what we're doing now. You know how to set up the table and figure, right?
It's where you just choose numbers and include.
Yeah, I would say for x approaching 0 from the left-hand side. All right, Rodney's here. Doubled our class size. All right, good deal. Okay. So I would choose points like from the left-hand side, minus 0.1, minus 0.01, minus 0.001. Those are getting close to 0 from the left. And then do the same thing from the right, 0.1, 0.01, 0.001. Now be sure you're in radian mode when you do that, okay? All right. And see what happens. I'm going to, I shouldn't do this, but I'm going to. I'm going to show you how I would approach this analytically. I'm not even sure it's going to work, but I'm going to give it a shot, okay? I'm going to take our function here, cosine theta minus 1, okay, over theta. Now, I'm going to do something that's rather strange. I'm going to multiply this by its conjugate. I know that's not in the denominator, but I'm still going to do it. Multiply that by cosine theta plus 1. But if I multiply the numerator by that, then I'm also multiplying the denominator by cosine theta plus 1. Okay? Now, what does that produce? Cosine squared theta minus 1, right? You get that? Over theta times, that's supposed to be a theta, not a 0. Okay. Theta times cosine theta plus 1. All right. I don't think this is going to help much. I had hoped it would, but I'm afraid it won't. Now, it might still. No, I don't think it will. So I think you're just going to have to do the plug and chug on that one. Because what I was going to suggest here, this becomes, and you don't know, well, yes, you should know it. You've had your trig. I know Rodney should know this, because I know who he had for trig. That's the same as minus 1 minus cosine squared theta, right? And 1 minus cosine squared theta is sine squared theta. So, but you still, you see, you still wind up with a 0 over 0. So that doesn't help you any. I thought it would. It doesn't. So don't sweat that. You're just going to have to plug and chug on that. Okay? And I think, did you look in the back of the book for the answer? Okay. Huh? Okay. I'm just going to cheat a little bit and look back here before I say too much. 23. Yeah, that limit does exist, and the limit happens to be 0. Okay? But you would have to plug in all your answers to see. And if you were to plot that, would be another way, and using a graphing calculator would be perfectly fine too. But if you plotted that, cosine looks like this, right? At 0, it's close. So 1 minus this would then be something that looks like this. 1 minus this flips it over, kind of. Okay? Now, theta, that's your identity function here. Okay? Now, and this is just really qualitative, it's not quantitative. Notice here, the numerator is staying close to 0 much longer than the denominator is. The denominator basically just crosses 0 here. This one is staying close to 0. So anything on the right side of this is going to be approaching 0. This is approaching 0. That is too, but this over that is approaching 0 much faster than this would be. Over here it's approaching 0 from the right, no, approaching 0 from the negative side here, because it's the ratio of this small number to this number here. So that's approaching 0. So yeah, both of those will be approaching 0 from the left and the right, from the minus side, from the plus side. So that is going to be 0. If you plug in the numbers in the tables, you'll see that. But also, if you use the graphic calculator, you'll see it. At 0, it's not defined. You'll have a hole in the function there, but that will be 0. So I do believe that. But I can't think of an analytical way to do that. Sorry. I'd hope that other would, but it doesn't. It just comes up being 0 over 0 still. Actually, there is a way, but we haven't gotten there yet. Now that I think about this, okay, so this will be minus sine squared theta, okay, over theta times cosine theta plus 1. Yeah. Now that I think about it, is. And this will be sine theta over theta times a minus sine theta over cosine theta plus 1. Now, I don't think we've done that yet, but you can look this up and find out this is indeed equal to 1. Okay? This is equal to, as theta is approaching 0, that's going to 0. But as theta is approaching 0, this is going to 1, and that's 1. So this would be 0 over 2. Minus 0 over 2. Who cares? It's going to 0, that's going to 1. So the product is going to be 1. Is 0. Yeah. So that's how you can prove it. I stopped too soon. You can't. But on the other hand, we haven't done that part. Sine theta over theta is equal to 1. I don't think we did it. We will do it in the future. Let me just go back and look. We didn't do that, did we? Yes, we did. We did it in example at the very beginning of 2.2. Yes, so you could have done it analytically. I wish you were back here, but you're going to be listening to it anyway. So there is a way to do it. That did it. Okay. Sorry. Any other questions? Okay. We're getting ready to start 2.3, and I think I have it up here already. So let me erase all this ink. But the problem is, this isn't, I think I opened 2.2. Okay. I opened 2.2. Sorry about that. We're supposed to be in 2.3. Huh? What? Limits? Well, to do derivatives, to do anything in calculus, you have to know what limits are. So those are the building blocks. Later we'll do them without doing limits, but that's where we get them from, is limits. So this is all preliminary that we really don't need. I'm sorry to say it that way, but we don't, except to, I went to the wrong section, sorry about that. Should be in 2.3. So that's where I'm going now, if it'll ever open. Okay, so now we'll do the slideshow from current slide. Here are our limit laws. I don't think I'm going to be able to blow this up, but let's see if I can. I won't be able to blow the whole thing up, but I'll be able to blow a portion of it up. I think I'll blow that portion up, just to make it a little easier to read. Okay. Limit laws. What if you know, this is the if, you assume this, that the limit of alpha of x as x approaches c exists. That does have a limit. And the limit of g of x as x approaches c also has a limit. Maybe different limits, but both of those have limits as x approaches c. Then, what this says, the sum law, the limit of the sum of two functions has to also exist, and what would that be as x approaches c? It would be the limit of the sums. That this exists, and that the limit of the sum of two functions is the sum of the limit of two functions. So say if this was L and that was M, then this would be L plus M. Okay? So here's what the sum law says. Number one, if you have two functions, you know both of the limits exist as x approaches c, then the sum of those two functions, their limit exists, and the limit is the sum of the limits. Okay? The limit of a sum is the sum of the limits. Constant multiple law. For any number k, okay, as x is approaching c, k times alpha of x. We already know that alpha of x has a limit. What if you multiply k times it? By the way, Nicole, I did find out that what we started on before did produce an analytic solution. I went on and did it, so if you listen to Screen Math, you'll see it. I had forgotten that we had already done sine x over x. And that's what it led to. That's the first thing we did in 2.2. Okay. So the first limit law is the sum, if the limits exist for f and g as x approaches c, then the sum of those two functions also exists, and that would be the limit of the sums is the sum of the limits of those. Constant multiple law, for any number k, no matter how huge k is, as long as it's a number, 4,585,963, that's fine. You know, as long as it's some number, then for any number k, the limit of k times this function, which has a limit, as x approaches c, that also exists, even though you're multiplying by an enormous number. Okay? And the limit of that would be k, you can pull the constant outside, the limit of a constant times a function is the constant times the limit of the function. We already said this exists. That may be a huge number. Just multiply by the other huge number. It's an enormous number, but it does exist. That would be your answer. They work for small numbers too. Okay? The product law. Remember, we assume that f of x and g of x both have limits as x approaches c. So, what if they're both huge numbers, but they do exist? What if you multiply them together? They'll still give you a huge number, but the limit of a product of two functions as x approaches c, if those both exist, then the product exists, and the limit of the product is equal to the product of the limits. So whatever the limit of this one was, multiply it by the limit of that one. That's what the limit of the product is. Now the quotient law. You know both of these exist. The limit as x approaches c, as long as the limit as x approaches c is not 0. Here it existed, that's all we said. Now we have to have the additional requirement, it exists, but it can't be equal to 0. Then, if that's true, then the limit of the quotient also exists. And the limit of the quotient is the quotient of the limits. Okay? As long as that limit isn't 0. Okay? So, the function may be 0, just not at c. Okay, then that wouldn't make any sense at all. The limit of g of x as x approaches c can't be 0. But as long as it's anything else, the limit of the quotient is the quotient of the limits. Okay? All right. Then powers and roots. If p and q are both integers, okay, it could be positive or negative integers, but just with q not being equal to 0, integer but not 0, then the limit as x approaches c of f of x raised to the p over q power. P and q are both integers, just as q is not 0. That also exists, and how do we calculate it? The limit of that thing would be the limit of the function raised to the p over q power. As long as you can do that power, you can take the limit of the power is the power of the limit. Okay? Now, furthermore, assume that the limit of x approaches c of f of x is always positive, never negative. Okay? Could be 0, but never negative. And q is even. Okay? So this q is an even number. Okay? So you have this value being non-negative and the q being even, and that the limit as x approaches c of f of x is not equal to 0. So here it says the limit of is greater than or equal to 0, and that the limit of, I think, and that the limit as x approaches c of f of x is not 0 if that ratio is negative. So, if this ratio P over Q is less than 0, then it has to be that the limit of alpha of x can't be 0. It could be 0 here if Q is even, okay? But it can't be 0 if that, but still it's going to be positive, okay? In particular, for n being positive integer, boy, they're putting so much into this one. It's really not as bad as it sounds, okay? For n as a positive integer, this is your power here. The limit as x approaches c of alpha of x raised to the nth power. Okay. Now, n is a positive integer. So obviously, this P over Q here is, we're forgetting about that. That says it's less than 0. So we're doing n positive here. Okay. Then this will be boy, this is, the way they worded this is so strange. So P and Q are integers, Q not 0. That makes sense. Then that's true. Okay, that's the first part. Now, for the second part here, that's true for this part up here. Okay, for the second part here, we're going to assume that alpha of x is greater than or equal to 0. The limit of c approaches, x approaches c, alpha of x is going to be positive. And q is even. So this is making sense so far. And that the limit as x approaches c of alpha of x is not 0 if p over q is negative. Okay. So those all fit, okay. In particular, now here's where they turn stuff to treasure. If n is a positive integer, so basically they're saying if that P over Q, not as that's a 0, so a positive integer, P over Q happens to be that Q will go into P a whole number of times. Okay? So that's going to be the first case here. Then the limit as x approaches c of alpha of x raised to the nth power, same as this. That's going to be the limit as x approaches c of alpha of x raised to the nth power. In other words, if the P over Q is a positive integer, this is true for anything as long as Q is not 0. It's certainly true if n is a positive integer, if P over Q is n. Now, let's go to the next part, this one. Now we have n's a positive integer. I don't see how this has anything to do with this much. Okay, n is a positive integer. The limit is x approaches c of the nth root of alpha of x. Now remember, alpha of x is positive if this, I think they mean here, I think this works a lot better if they said n right here. N is even. If they said that, this is perfect. Because you're not using Q anywhere down here, so why are they even mentioning it? Okay? Unless this is really poorly put together. And if you'll notice in your book, they don't have this last part. So obviously this was a screw up in the previous edition. This is still true, but it makes no sense. If you start with P over Q and then go to N, it just makes it confusing. Okay? Separate these two things. In this one right here, that works for here. Then start a new line here. I would say make this 6. Okay, if n is a positive integer, then this is true. And then what you need to do here is go back. If n is now even and alpha is greater than or equal to 0, then you can do this. Because you can't take an even root of the negative number. That's all they're saying here. As long as you can do this, then the limit of a root is the root of the limit. That's all they're trying to say here. In the second limit, assume that this is f of x is greater than 0 infinity. Same thing they were trying to do there. They sort of separated the p over q, left that up there, done the number 6 down here with n, and that would work. Okay. Trying to tie those together was messy, and in the new edition they don't do that anymore. Okay. Sorry about all that. Okay. Now, this is using that very last thing that we did, and sorry it's such a lousy slide. The limit as x approaches c of x over p, x to the p over q. Obviously here q can't be 0. Okay? And as long as q is at 0, then you can plug in and say c to the p over q. Here's the other thing you have to keep in mind. If q is even, c has to be positive. But as long as those things are met, that's true. Okay? As long as q's not 0 and if q is even, c is greater than or equal to 0, then everything works. All right. Let's do example 1, and I'm pretty sure that example 1 doesn't have a slide. No, it doesn't. They don't have any more slides. So let's do that. First one. Let me get my pen set up. All right. The limit as x approaches 2 of x cubed. I think you can all do that with no sweat, right? 8. Perfect. You just plug it in, okay? B, the limit as x approaches 2 of x cubed plus 5x plus 7. Say again? All right. It was 8 plus 17.
8 plus
17. That's an x cubed.
I did it as 8 times 5.
What's that? That's an x cubed. Okay. It's the same as this, only we're adding these two terms to it. And the limit of this, that would be 10 plus 7 is 17. 8 plus 17 is 25. Is that what you said? Good. I just don't hear well. Very good. All right. And then the next one. The limit as x approaches 2, looks pretty similar, of the square root of x cubed plus 5x plus 7. What would that be? 5, exactly. The square root of 25 is 5. Perfect. And basically, you were using the limit laws where you thought about it or not. You were just plugging in. But you were plugging in as you summed them and took a square root of them. It all makes pretty good sense. So all that weasel words at the bottom there, you would have seen if any of those didn't fit. Like if this were to come up a negative 25, you said, no, you can't do it because you can't take the square root of a negative number. Okay. That's all those other things are doing. Now let's see if they got it right. They got 8, they got 25, and they got 5. Good for them. Let's see. Example 2 they don't have either, so I'm going to do example 2. Evaluate this one. The limit as t approaches 1 from the left-hand side, from the minus side, of t plus 6 over 2t to the 4th. What would that be? Oh, I'm sorry, I misread the problem. Sorry. I was going to say, why did they do that? They didn't do that. I misread it. That's a -1, not T1 from the minus side. It's T approaches -1. All right, can we do that? It would be what? T plus 6, right, over 4t, 2t to the 4th. Numerator would be? Yeah, 5. Denominator would be? Okay, as t approaches -1. -1 to the 4th power is 1, multiply 2 times 1, 5/2. Say that again? No. Only if that was in parentheses. Remember please excuse my dear Aunt Sally, I don't know what they did. You do exponents before you do multiplication. Right? So you exponentiate first, then you multiply. Okay. Good deal. And then the B one here, and by the way, they got 5/2 too, good for them. Now they do the limit as t approaches 3 of t to the -1/4 times t plus 5 to the 1/3. Huh? What are you getting at here? Okay. Well, let's try it. Plug it in, plug it in. What do you get? What do you get? Don't worry, you can't evaluate the 4th root of t. Okay, so just, yeah. What would that be? 4th root of 3. It would be 3 to the -1/4. Don't try to evaluate it. Just write it down. Okay? The next one you can evaluate. What would that be? 3 plus 5 would be 8, and that's to the 1/3. What do we mean by this? That would be, of course, a minus exponent moves it downstairs. So this would be 8 to the 1/3 over 3 to the 1/4. Right? You know what 8 to the 1/3 means? Yes, you do. It's the cube root of 8 to the 1st power. Oh, yeah. And this would be the 4th root. Yeah. That would be the 4th root of 3, which I don't know. It's an irrational number. But I know what the cube root of 8 is. Don't you?
It's 2, right?
2, exactly. So this would be 2 over the 4th root of 3. Or you could have the way the book did was 2 times 3 to the 1/4 power. 1 over 3 to, or something like that. Yeah, 2 over, yeah, they say 2 over 3 to the 1/4 power. You can write it 3 over the 4th root of 3. I mean 2 over the 4th root of 3. It's the same thing. But they started the problem with exponential notation, so they didn't go to radical notation. I just did that so you would see what the cube root of 8 was, what that meant. But I would leave it in that form. It doesn't matter. Either way will work. And we got it right. Good for us. Okay?
And you will vote this in.
What's that?
You will vote this in.
Yeah, I will have this uploading onto YouTube as soon as class is over, and then I'll try to move it to the playlist probably this afternoon sometime.
And if I have any questions, I can email you or say to the next class.
Yeah, that would either will work. Yeah, if you happen to be on this campus before you can see me then too. I didn't think you would be. Okay.
It's a drive out.
Yeah. All right. All right, we just lost both. Rodney's back. Good. Okay. Oh, I see. Okay. I knew you came up here, but I didn't see what you did. All right, one more example in this section, and we're through with this one. This is a very short section. Whoops, that's not what I wanted. What's that? Okay, wait just a second. Let me see if I can remember how to. Yeah, okay. What was that again? The fourth root of 3? That's just one way you could express this, or you could leave it in this form. The answer they gave was this one, but this is the same as that, the fourth root of 3. It's an irrational number. I don't know what it is. It's 1 point, some pretty small fraction, I think. If you got a calculator, you can plug it in and see what it is, but it's an irrational number. But the cube root of 8 is not irrational. That's 2. Okay, that's why I had to do that. So let's do number 3. Can I go on and erase this one? Okay. Erase the ink. And number 3. Example 3. Show that the product law cannot be applied to this one. The limit as x approaches 0 of alpha of x times g of x if alpha of x is equal to x, no problem there, and g of x is equal to x to the minus 1. Okay? Can you apply this product law? Well, the product law would say that would be x times 1 over x, and that would be 1, and that limit we would say would be 1. But the product law requires that both of those limits exist. And limit of alpha of x equal x exists as x is approaching 0. That would be 0. But the limit of g of x as x approaches 0, g of x is 1 over x. That doesn't exist. That would be infinitely large coming in from the left, infinitely small coming in from the right. No, I said it backwards. Large coming in from the right, small coming in from the left. Going to infinity either place, no way that exists. So you can't use the limit law if both limits don't exist. So that's what the deal was there. Okay? So the limit law did require both of them to exist. So that's it for 2.3. Let's look at the preliminary questions. State the sum law and the quotient law. Well, you can go look right above you there. Oh, you don't have your book with you. Basically, the sum law, the limit of a sum is the sum of the limits. As long as both of the sums have limits, okay? Same thing for the quotient law. As long as both factors in the quotient have limits, then the product of a limit, the limit of a product is the product of the limits, as long as those limits exist. So I don't know if they did that in the back. I'm guessing they probably didn't, but let me look and see. 2.3. Yeah, they wrote them all out. Okay, so the only difference is, oh, the quotient law. I said the product law, the quotient law. The quotient law does have one more thing in it. Not only do both limits have to exist, but the limit of the denominator can't be 0. That's the only other part you have to have. I was, for some reason, read it product law. Okay, number 2. Which of the following is a verbal version of the product law? I guess that's what I was looking at, assuming the limits exist. The product of two functions has a limit. Well, if both limits both functions have limits, then yes, that's true. But the second one says the limit of the product is the product of the limits. That's also true. The product of a limit is the product of functions. No, that's not what it says. It's the limit of the product of the functions. Okay? And a limit produces a product of functions. No, not necessarily. So I would say A and B were both probably true. Let's see if we can find that. They just say B. Well, B says more than A does, but I think they both say part of that, but we'll let them get by with that. Okay, then let's look at number 3. Which statement is correct? The quotient law does not hold if the quotient law does not hold if A, the limit of the denominator is 0. Okay? B is the limit of the numerator is 0. Which of those keeps the quotient law from working? Which one makes the quotient law not work? A, of course, because it's the denominator that can't be 0. The numerator doesn't matter. Okay? And sure enough, 3A is correct. So homework exercises in 2.3, any of the odds 1 through 23. They jump off with a lot, but those are pretty easy to do, I think, most of them. Okay? Then do 25, it's the only one like that. Then do either 27 or 29 or both. And then do any of the odds 31 through 35. Okay? You can look at further insights and challenges if you really want to do that. Okay. And this does end the PowerPoint for 2.3. Let's move on to 2.4. In spite of doing all we did at the beginning, we did finish that. So let's end that and move on to 2.4. And I think, if I'm not mistaken, I believe it was Nicole that asked something about continuity before, and sure enough, that's what we're doing now. I said we would be getting to it. I think she was the one who asked, and here is where we're going with that. Okay. My eyes are so dry. Now, in everyday speech, the word continuous means having no breaks or interruptions, right? Like if he's just talking continuously, he's not giving you a chance to answer a question, ask a question. All right, yeah. That wouldn't apply here, would it? Okay. No. Okay. In calculus, continuity is used to describe functions whose graphs have no breaks. If we imagine the graph of a function, f, as a wavy metal wire, then f is continuous if the graph consists of a single piece of wire as shown in this figure. If that's your wire, or that's the graph of the function, and every little pink pixel on that graph is defined, then, and everything between every pink pixel is defined, then we say f is continuous. At least within that, specifically it's continuous at point C, because all the values on the left and on the right are defined and continue and fit and C itself. fits. Okay, that is a continuous function. Okay. Most physical phenomena are continuous in nature. In fact, it's very hard for them not to be. If you were graphing the temperature of outside here, you would see it probably is warming up outside. It's not jumping up a degree at any time. It's warming up slowly. Depending on how precise your thermometer is by every thousandth of a degree, whatever it is, it's continuous. Even as one of those old dials there, you don't see it just jump over here. It moves over there very slowly. Temperature is a continuous function. Generally, just about everything we deal with is a continuous function. Black holes, I don't even know what they are, okay? So they may not be continuous, but most things would be continuous functions. Okay. Now, a break in the wire, if you're thinking wire, if this was our situation here, this would not be a continuous function. If that wire actually does have a break in it. Like this. So it goes along like this. Everything's connected. All the pixels are next to each other, just adjacent to each other, right with them. And at C, the value is here. But just past C, it jumps up to here. So it's f of x. Oh, I'm sorry, it's G here. It's the G of C is one functional representation here, but a different functional representation there. That's not a continuous function, because at C, it's the limit from the left is not the same as the limit from the right. Oh, limits are involved here? Yes, they are. So that's how we define continuity. If a function at a point, the limit of the function at that point from the left or the right is the same, that's a continuous function. If they're not the same, it's not a continuous function. But not just that. I'm sorry, there's one more thing. If you just had a hole in the function there, it would be, the limits would be the same, but it would not be continuous because there's a hole there, okay? So there is one problem there. If there's a hole in the function, it's not continuous, okay? So here's our definition of continuity at a given point. All right. Assume that f of x is defined on some open interval containing the value x equals c. Some interval that contains that c. That f of x is continuous at c if the limit of f of x as x approaches c from the left, from the right, is equal to f of c. Okay? It's continuous at c if the limit as x approaches c from the left and the right is f of c. Okay? Now what that means, of course, is left and right hand limits both exist. Of course they have to, but not only that, but the value of the function is, see, before we were saying except maybe at c, now we're saying f at c has to be defined, and if it is, that has to be the limit. Okay? If the limit does not exist, then that's not true. Okay? If the limit as x approaches c of f of x does not exist, if it this area here, that way there, doesn't exist, then this isn't true. Okay? Or if it exists but not equal to f of c, then we say that f of x has a discontinuity or is discontinuous at x equals c. Okay? And let's look at a couple of examples of that. Okay. Now this first one is just patently obvious. Okay. Here's a function. This is the constant function. F of x equal to k. Whatever that k is. Okay? That's a continuous function because it's always, no matter what x value you put there, f of x equals k. It's got to be continuous. That's horizontal line, goes forever. It could have been a negative number. Didn't matter, wherever it is, it just continues forever. It could be 0. That's continuous, you know. That's a constant function, a continuous function. Okay. Need a key? Oh. Okay. Now, next. This function is the identity function, g of x equal x. For any value x, you got is g of x. Same number, same value, okay? That's a continuous function. Always and ever, now and forever. For any value x, g of x is equal to that value. That's a continuous function, okay? Now, weird ones now. All right. This function is this wire here, except that right there, its value is up there, 10. The limit as x approaches 2 from the left and from the right is 5. But at x equal 2, it's at 10. That's obviously not continuous, because the limit of f of x from the left or the right is equal to 5, but the value of f of 2 is 10. So obviously that's discontinuous. However, that discontinuity is renewable. Redefine it at the one point, and redefine it as 5, that makes it a continuous function. So that's what we call a removable discontinuity. If you redefine f of 2 to be 5 rather than 10, then it fits the curve perfectly, everything fine. Okay? So this is discontinuous. F of 2 is not equal to the limit as x approaches 2. Okay? This one is because you change the value f of 2 to make it the limit. Now let's remove discontinuity. Okay. And I can almost hear you say, so what? You know, but it's still true. Let's see. This one, however, is what they call a jump discontinuity. This function has a limit as x approaches 2 from the left. It has a limit when x approaches 2 from the right, but they're not the same. Okay? Now the function is given a value x equal 2 to be down here, and that is its limit from x approaching 2 from the left, but it's not the value for x approaching 2 from the right, so this is a jump discontinuity. There is no value you can put in there here to make that continuous. Because they just are separated, it's a jump discontinuity. The left is continuous at x equal 2, the right isn't, and there's no value way you can make that happen. Now, this is also a jump discontinuity, okay? But in this case, the limit as x approaches 2 from the left is a value. The limit as x approaches 2 from the right is a different value, but f of 2 is at a different value completely. Now, again, there's no way you can reassign f of 2, even if you tried to do the point right in between. Still wouldn't be continuous here or there. So that's a jump discontinuity. Neither the left or the right hand functions are, they're neither left or right continuous. This is left continuous because the f of 2 is the limit of f of 2 as f is approaching from the left, but it's not right continuous because the limit of f as x approaches 2 from the right would be here, but f of 2 would be down here. These are neither left continuous or right continuous because the value is neither one of those values. Okay. But those are both discontinuities. And I think we're out of time. Sorry about that. I think the next slide is this one. So we will hit this definition next time. Let's see if we got far enough along in 2.4 to have any homework exercises. I kind of doubt it, but let's see. Never mind. Okay. Yes, you can do number 1. Okay. I think you can do 3. I think you can do 5. Okay. But I don't think you can do any beyond that. So just do 1, 3, and 5. Okay. And what we had in 2.3. All right, good deal. Have a good week.